Here we go. Okay, so today we're going to begin looking at one of the more infamous machine learning data structures, the artificial neural network. So, okay, that really is an R. There we go. The artificial neural network. So I'm going to begin by talking a bit about the underlying biological inspiration of the artificial neural network and how it relates to the idea of a logic gate and a lot of why this model was found compelling as a computing topic as early as the 50s. We'll then talk a little bit about how things went very badly for neural networks for a while and talk about how the badly got solved. And we'll see where we get. So before we think about an artificial neural network, we're going to scoot over here and think a little bit, just a little bit, about the brain, specifically with reference to neurons. So within the brain, there are extraordinarily large numbers of neuron cells. And so each neuron cell is characterized by lots of connections from other neurons, all coming in to the neuron, and then it has connections going outward from it. And so, it's been observed in various experimental studies and the like that if the combination of inputs is somehow very active. And so when we talk about the combination of inputs, what we're actually talking about is electricity flowing along these organs. So we've got little electrical charges coming on through here. And if there's enough of those accumulated charges, then we say that this neuron will fire. And when this neuron fires, it means that electricity gets propagated outward from it to all of the other neurons to which it is connected. As you might imagine, when you're talking about the human brain, these interconnections are somewhat complex. Okay, by somewhat I mean massively complex, in fact. Tops of your heads, anybody know how many neurons are in a typical brain? I think connections works out to trillions. I think it's something like 100 million or thereabouts. So it's a lot. It's a lot. But in a sense, a lot of the intellectual content of the brain is stored in how they are interconnected. So what do I mean by this? Well, let's imagine something sensory happening, okay? So specifically, we're going to focus on the eye. So as we know, light comes in to the eye. And the eye does something with the light. That is, the eye contains some lenses, or a lens, and it also contains an aperture, the pupil, that permits the light to come in. And as you know, if you get overwhelmed with a whole lot of light, that pupil, that aperture narrows, and if there isn't a whole lot of light, it widens so it can gather more light. In other words, you can think of the pupil as kind of a control device that throttles the light. Now, the light makes it through the pupil and then makes it onto the surface at the back of the eye, right? The retina. This is as much biology as I am comfortable discussing. And even this is kind of at the limit. But anyway, so what's the deal with the retina? Well, the retina is this surface that has lots and lots of connections back to neurons. over in the brain. And these are all really, really complex. So we'll just take my word for it, complex. But the point is, the biology of this, and now I'm definitely going beyond what my knowledge of biology permits. Somehow the biology of this causes motion in the retina that is then somehow transformed into electricity. And that's how the process begins. That is, when we're thinking about the brain getting information about the world and deliberating about that information, we first have to start with something physical in the world, right? So that thing that's physical in the world gets to the retina, and the retina stimulates the neurons, and then little electrons start flowing down them. And now they're in the brain, the network. And it's a very complex and involved network. But I think you all can already begin to appreciate why the idea of working out a computational model of the neuron was so absolutely captivating. Because it just seems so natural. And we're really going to get in and see how that natural it proves to be. So, this stuff flows in. Now, the brain, of course, is very, very complex, and these signals go in all kinds of directions. Just to think about one pertinent example, let's think about our friend the pupil that's throttling the light. The degree to which the retina experiences excitation goes through, a bunch of neurons and comes back to the pupil and then sends electrical messages to the muscles that control the pupil to achieve that throttling effect. Fortunately for all of us, that is completely unconscious. You do not have to use your deliberate thought processes to throttle light through your pupil. That sounds unpleasant. Anyway, so the brain takes care of most of this for you. And in fact, most of what the brain does is completely unconscious. Okay? I'm going to say right here that nothing about studying neurons is going to teach us a whole lot about the phenomenon of consciousness itself, which is astonishingly difficult to study. And we'll get to that, from time to time periodically. But what we're looking at when we build these models is to talk about the transmission of information in the nervous system and how we can model that computationally. Now, this model of how the brain functions and how information is transmitted by neurons that get activated and so forth, improvements in neuroscience in recent years have shown that the model is inadequate to explain the brain. In fact, you can think of the brain as being immersed in something of a chemical bath, and that a lot of the computation actually happens through chemical messages sent through this liquid bath that can actually reach various regions of the brain, even without direct neuron connections. So whenever we think we've got a grip on, the brain works this way, it then turns out to be even more complicated. Great fun for researchers, kind of frustrating when you think you've got it under control. That said, this neuronal model has proven massively, massively influential in computing and in AI, and continues to be so to this day. So how do we turn all of this stuff into a data structure? Because ultimately, that's what we do. So let me introduce you to the first, or at least earliest significant, maybe people came up with other things before this got published, but essentially the first type of artificial neuron that's been proposed. And this is called the perceptron. The perceptron. So what's the big idea with the perceptron? We can think of this and really any other kind of neural network as being a directed weighted graph in discrete math terms. It's a directed weighted graph. In other words, we've got nodes, and for now we're going to call these nodes the inputs. And so thinking back to the example of the eye, these inputs are getting data from somewhere, where specifically is not overwhelmingly important. Okay? So far, so good. And then there are the outputs of the inputs. And those are the next stage things that they're connected to. And so what we then imagine is every node in the input layer has a directed connection to every node in the output layer. And you wind up with a drawing that looks something like that. And when we're talking about artificial neural networks, you're going to see this kind of drawing quite a lot. Now, at first glance, compared to something like a brain, this looks pretty lame. Now, why would I make such an obnoxious claim that this looks lame? In the brain, we're imagining huge numbers of levels of interconnections after interconnections, sort of trailing on, going on and on and on, right? This is one level. That looks kind of lame. You're not going to get a whole brain into that. But you can certainly get something interesting. And it makes a great starting point. Ultimately, of course, we're going to find that this does wind up being just a component of a larger entity, but not quite yet. So if you examine this network of inputs and outputs, if we think about it in somewhat more mathematical terms, we can imagine that each of these outputs up here is really representing a function of their related inputs. So in other words, if I know all the values from the inputs, I can determine my output. So even though this is sort of a nice, pretty interconnected network of perceptrons, it's not actually as interconnected as it looks. That is, each of these outputs has a state that varies independently of how the states of the other outputs are determined. So when we're thinking about a perceptron, this is sort of a perceptron network, but we can think about a single perceptron as some number of inputs. Let's just go with 2 for now. And an output. That looks something like that. Now, for those of you that have taken or are taking a computing organization, where have you seen something that looks like this before?
Circuits.
Circuits. You look at it and it's like, that could be an AND gate. Or it could be an OR gate. Or it could be exclusive OR. It could be any number of things. Isn't that cool? Okay. So, primed with that idea, let's think further about what this looks like as a data structure. Okay. So, each of these edges has a weight associated with it. And thinking about the concept of an activation in a neuron, essentially what we're wanting to do is to find out if the weights exceed a certain threshold value, it's active. But if the weights are below that threshold value, it's not. Again, ghosts of circuitry, no doubt, are coming to mind. If a neuron is either active or not active, that suggests that it's just like a digital logic gate. And that's when the computing community was like, whoa. If logic gates can map directly to neurons, which we've now learned they can't, but let's just go with it. But if logic gates can map to neurons, and neurons are really just binary digital circuit elements that happen to be biological, then in principle, I could build a machine that imitates a brain. Now, there are certain limitations here. If a brain has 100 million neurons, that's a tremendous amount of simulation for our poor computer to do, especially when you consider the number of connections between them. But, people have long had imaginations of building some kind of massively parallel machine that can handle all of this. These days, the massively parallel machines they tend to use for this are GPUs. the neural network community has become infamous for hijacking the GPU in the computer to use it to learn instead of to graphic. Very interesting. We won't be doing any GPU programming in this course. That's its own somewhat difficult mess, but you at least gain an appreciation for why it would be helpful. When you again think about the circuit analogy, we know that when we build a digital circuit, everything on a given clock cycle essentially happens in parallel, right? All of these gates just are receiving this flow of electricity at the same time, and it's then kept synchronized by the pulse of the clock cycle of the CPU. So yeah, the connections then between the neuron and the digital computer appear to be profound and then encapsulated by the idea of the perceptron. Okay, so let's think about it as a data structure. Well, this specific perceptron could be represented as an array with two elements, W1 and W2. I mean, we all know they're actually 0 and 1, so just forgive me. I just reverted to my normal person counting mode for the moment, okay? So I've got these two weights, and then I can have another array that represents the inputs. So I might call that in1 and in2. So now what I do is I just do some multiplying. So I can say my input 1 is multiplied by my weight 1. My input 2 is multiplied by my weight 2. And then I add those, and I get a sum. And that sum is in turn passed through some kind of a threshold function to determine whether I go up or down. And bam, there we are. That is the perceptron. Yeah, David. What was the up or down part of the threshold? Oh, I'm just saying if the sum is above the threshold value, the output is a 1.
And that means that the output's going to be passed to the next connection?
Right, if there is one.
And if there is one, then nothing gets passed, and nothing goes to the next one.
Exactly. Yeah, good. You know, so the thought here ultimately is that inputs are connected through a big network that eventually lead to outputs, where inputs ultimately represent our senses and outputs represent our muscle motions. So that's kind of the ultimate goal of what one would do with a neural network. You may find it fascinating how infrequently that goal is achieved. As we're going to see, it's much more common for these to be used simply as straight classifiers. Along the lines of what we worked on last week. But there we are. Okay, so that's the whole thing. Well, where's the learning? The learning consists in adjusting these weight values so that for a given set of inputs, it matches a target output. So let's imagine what that process looks like. You know, I've only got 2 of these. I can probably pretty comprehensively specify an input. If I've only got 2, right? It's not so hard, right? Okay. Glad we're all on the same page on that. So let's imagine a comprehensive specification of a behavior I seek for it to exhibit. And here is, drum roll please, that comprehensive specification. I'm going to make a table. For those of you who have taken or are taking computing systems organization, this is going to look shockingly familiar. So, what is this? It's saying I want the neuron to fire if both of its inputs have fired. So, what would that look like? Well, what I'm going to do is I'm going to say, well, that means I'm going to make W1 1.0, W2 is going to be 1.0, and then what about my threshold? Well, what do you all think? What should my threshold be?
0.0.
Say my threshold is 2.0. Yeah, that could work. What could also work would be like 0.5, 0.5, 1.0, something like that. So there's the fascinating issue of how do I get there? Let's find out. So initially, let's say W1 is 0 and W2 is 0 because they're just lame. So I am going to take all of my training inputs and all of my outputs, and for each set of training inputs, I'm going to calculate how wrong is it. Okay? So let's just play around with this a little bit. I put in 0 and 0, I get 0. So I'm going to create, some errors here. Okay? 0 and 0 is, I got 0. My error is 0. I just subtract them, right? Now I've got 0 and 1. And 0 and 1 gives me 0, right? Because both of my weights are 0, and so it just gets multiplied by 0. So what's my error? So my error is going to be like a 1. My target minus the actual output. And then with 1, 0, I get that same error. 1. Yeah. Back to
the other second. You said 0, 0.
Yeah, 0 and 0. I get multiplied by 0 and 0, give me a 0, and I want a 0, and so life is good.
Yes.
Oh, I made a mistake. I was believing this was an OR gate. I don't know how I tricked myself into that. Thanks for catching it, Innocent. Actually, right, you get 0 and 0 times 0 and 1, you get 0, no error. Okay, yeah, no, life is good. Life is good, okay. And then you get 1 and 0 times 1 times 0, and you get no error. Life is good. And then you've got 1 and 1, and you want a 1. And yeah, now I've got my error of 1. So what am I going to do? Well, what I'm going to do is I am going to adjust each weight based on the errors it received. So one way we can think about this is we can take these 4 error values and find the sum. And that's like the total error in the network. Now, for each input case, what we're going to do is take that error value here and multiply it back by those input values to determine the updates I'm going to make to the weights. So if we start with this top case, I multiply 1 times 1 and I get a 1. And so W1 is now 1. Then I get 1 times 1 and I get a 1, and W2 is now a 1. And now I go to this next case. Well, in the other cases, there were no errors. Yeah, David.
So that, so the reason why you're changing the weights is because as it's going through the weights, it was originally 0, 0, and you're expecting it to be a 1.
Yep. But it's not. Because the weights start with arbitrary values. I just picked zeros for the heck of it. You could actually make them random.
So is the output saying that's what the output is, or is that what the expected output was?
These are expected outputs.
Okay.
But because these are both zeros, all actual outputs were 0.
Okay. That makes sense.
Yeah.
So this is supervised then?
Very supervised. Yes, yes. Great point. Yeah, this is totally supervised learning. Yeah. In our next project, we're going to look at a different type of neural network that gives us unsupervised learning. But yeah, this is absolutely supervised learning. Yep. Okay, so now they're both 1s. So let's see how it does, right? So we go, let's compute our errors again. And as we compute our errors, we have 0 times 1 plus 0 times 1 gives us 0. Guess what? No error. Life's good. Then we get 0 times 1 plus, we get 1 times 0 plus 1 times 1, and that's 1. And so expected minus output gives us 0 minus 1. That's going to be an error of negative 1. Then we get 1 times 1 plus 0 times 1 is 1. Expected is 0. 0 minus 1 is negative 1. And then finally, we get 1 times 1 plus 1 times 1 is 2. And so then 2 minus 1 is 1. And that yields a total error of negative 1. Now, something you might start to be worried about at this point, and if you're not worried about it yet, you really should be, is that this is really going to cause our weights to fly back and forth at an astonishing rate, right? So now I take my 1s and I multiply them by negative 1, and my weight 1 is now 0, and my weight 2 is now 0. And then I take my negative 1 times that 1 and negative 1 times a 0, and then my poor weight 1 is down to negative 1. And then I come back and do the same thing for the other combo. No, that's negative 1, yes.
Explain again what's happening. You start by the first one, you multiply by.
Yeah, so I'm taking my error value,
Mhm.
I multiply it by my input values, and I add it to the weight.
Which weight? Because there are two weights.
The weight of the corresponding input.
Okay.
Yeah, Jake.
For the second one you did, should the last one be negative 1 as well? Isn't it 1 minus 2?
Oh, that's a good point. So this is going to be even worse. Yeah. That's right. 1 minus 2 is actually a negative 1. And so this is actually negative 3. And so each of these is now negative 6. So a concern that arises at this point is that this thing is going to jump around like a maniac. Specifically, in this jumping around process, it seems less likely to actually ever converge on anything. And if you're worried about this being a problem, you're right. It is. And it's a known problem. So the solution to this problem is to introduce another variable, typically called alpha. This is the learning rate. And alpha should be in the range 0, 1. We never really wanted it 1. We certainly don't want it at 0. What we're going to do with this term is multiply this term by that update. Yes?
Could you just say how you go from your error, your sum of errors to a new weight?
Oh, sure. You take that error value, and then for each line here, you multiply the error value by the input and adjust the weight from that input to the output. You just add it.
How
Yeah.
does it give you the second weight? Like how? In this case, you took like 1 times 1
Mm-hmm.
plus 1 or minus 1.
Okay, in this case, for the negative 3 error,
Yes.
for this line, with this output, we had a minus. You know what? I mixed this up. I'm glad you asked about this. The errors apply separately for each row. You don't add them up yet. Whoops. Let me rework the example because I messed up this detail. Yes, I am unlearning.
The control of delete.
I am hitting undo. Yeah. All right. We're going to come back to our friend the learning rate once I actually do the example correctly. Okay. So let's come back here. Right. So these are your errors. Oh, no, not quite yet. These are your errors. These are your errors. Okay. Yeah. Sorry about mixing this up. Thank you for the questions. So let's fix this, right? So we look at the top row. We have 1 times 1 and 1 times 1 for each of those weights. So looking just at the first row, whoops, let's get our eraser off. you're going to have W1 equal to 1 and W2 is equal to 1 because we've added the error to that. Then what's going to happen is absolutely nothing else because for each of these errors, they don't exist. There are no errors. And so there's no further need to update the weights. Yes?
So for the new weight, just add the total error to the previous one?
Exactly. And so kind of where I was going with the next example before I mixed it up, but we'll go through it again, is that we get a different set of errors, right? And what we found was those errors were 0, -1, -1, and -1. Because now all of the weights are sitting there at 1. When the inputs are zeros, there's no problem. They each get multiplied by those ones, life is good. When you have 0 and 1, now your input is a 1. This is still sitting here at 0. You have an error of -1. Same thing happens there, and then here you got up to 2, and you have a target of 1 minus the 2, and you get a -1. Is that right? You have 0 minus 1, 0 minus 1. Yeah, that is right. 1 minus 2. So we're sitting on a collection of -1s. So now we're going to apply these errors correctly, which is still not going to be pretty, but slightly less ugly. So let's start with the -1. We have a -1 on each weight. And so this drives our weights as follows. So the weight started at 1, and now we're going to add a -1. Weight 2 started at 1, and now we're going to add a -1. Now we go to the next one. Okay, that is inexcusable. All right. That's much better. Okay. And same thing here. So we have a -1 multiplied by the input of 1 is a -1. But it's multiplied by a 0 here, so we only change weight 1. But now the same process happens on this line. We have that 1 times a -1, so weight 2 gets updated, and then nothing, of course, happens at the end. So at this point, both weights are now down to -1. Still bad, but not like -6 bad. Okay. But now the same thing I was saying about the learning rate still applies. We can see that this is just going to keep flipping and flopping back and forth, you know. And so the solution is this learning rate, alpha. And so this is a value between 0 and 1. If it's 0, no learning occurs. If it's a 1, we're in this exact situation. Why? Because we're going to take alpha and multiply it by each of our errors before we do the update. So what's a typical alpha look like? Well, imagine you've got an alpha that's something like 0.1. That's going to result in relatively small adjustments to these weights. Now, I could continue walking through this. It would kind of get a little dull after a while. I want to show you conceptually, though, how this works, why this ultimately works. What we have here is the following process. Let's make a graph. So you've got your A input, which can be a 0 or a 1, and your B input, which could be a 0 or a 1. Here at 1 and 1, we should have it be active. Then here at these points, it should be passive. Ultimately, what we're doing with the weights is defining a line, right? And the line we're ultimately looking for should have a slope and an initial position that looks kind of like this, so that it separates this from this. That's essentially what the training process consists of. In its ultimate form, which we'll get to a little bit later, it basically turns into Newton's method, more or less from calculus, in a very approximate way. But now here is where some trouble begins. Let's do another one of these little graphs. Let's say what I want is this. Where would I draw a line to build a good classifier for this function?
The one
I'm watching your arms. I'm trying to imitate them.
in between the two black dots.
What, like here?
Yeah.
Yeah. So that's cool. Let's do a couple more of these. Some of you may already be sensing that this is not going to end well. So how about this? Where's my line going to be? Okay, can you give me that sound effect again, Austin? Good. All right. That's pretty cool. Of course, now we're going to have a really fun one. Where am I going to draw the line?
Yeah, it's going to be screwed up, not real looking line.
Some kind of screwed up, not real looking line.
Yeah.
Not aligned by.
That's a circle.
A circle? Will the circle be unbroken? An ellipse. Ellipses are not lines. And let's think back about what this thing is doing. This is just a linear combination, right? However I separate them has to be a line. It'd be nice. We'll get there in a few minutes. But the point is, you just can't do this with one line. Can't be done. Yes?
So question, what exactly are we trying to achieve by tracing that line? Is the goal trying to make a line that it has like points above it or below it or what?
All points of one color should be on one side of the line. All points of the other color should be on the other side.
So, okay, there is this. I didn't see that one.
No worries. Yeah.
If you create like a squiggly line that
It can't be, what is that called when it has two x value, two y values for the same x value? It can't do that. It can't not be. Yeah, it can't not be a function.
Sure. Yeah. Vertical line. Well, yeah.
Cool.
We can approximate a vertical line by making it kind of close to vertical. But I mean, this isn't going very well, is it? So the argument I just presented to you came out in the 1968 book called Perceptrons by noted AI personality Marvin Minsky. Marvin Minsky, who was kind of a giant of AI back in the day. And so he wrote this book and basically said, perceptrons are useless because they can't do this. So neural networks, forget it. And they were forgotten for the next 18 years, as a matter of fact.
Was he still alive when it changed?
Oh, yeah.
Nice. That's nice.
So several of you have pointed out maybe some ways of thinking about this. Now, a lot of the appeal of the perceptron is that it was guaranteed to converge if a solution existed. Very if, right? But it was guaranteed to converge. So it was seen as this amazing machine learning algorithm, except that it was guaranteed to converge only in a very small number of cases. And obviously, we want to do stuff a lot more elaborate than an AND gate with this. A logic gate is just a way of talking about something we fully understand and seeing if, can this algorithm do something literally this dumb? And what we found is that if you try to exclusive OR, it can't even do that. If it can't handle a 2-bit exclusive OR, how do we expect it to determine whether an image represents a reality show personality or a member of a Star Trek race? Kardashians, Cardassians. It's so easy to mishear. So at that, people just gave up, right? Except some people didn't. So here was the big idea. Earlier, I showed you all, the idea of we've got two input. I mean, I did more than two, but this will demonstrate it, right? So we've got multiple inputs and multiple outputs, and it doesn't really get you anywhere. These are really two separate functions, right? Unless you do this. In other words, you can take a perceptron and have its outputs be the inputs to another perceptron. And at this point, what you have is a multi-layer perceptron. Interesting. Very, very interesting. So let's say I give you this multi-layer perceptron, and let's say I don't give you the weights. Here's a little puzzle for you. Can you just pick some weights so that this computes an exclusive OR on the output node? Just for fun, I'm going to break you all up into groups and see who can come up with it first. So front row, middle row, third row, and then back row. David, you just pick which two you want to sit with. All right. So see if you. So just to be clear, right? We've got 1, 2, 3, 4, 5, 6 weights. Pick 6 weights so this computes exclusive OR.
When you get something, we find different inputs, right?
Yes. Well, assuming it's the very last one, it's supposed to be the one that results in exclusive OR. So those two need to be different at the very end, in the middle. So we need some way of making those two, between the two interactions, two different values.
And it's not A and B, and not,
So, like,
no, it's just not.
So do it. So if you have A and B,
That makes sense.
to get A XOR B, it's gonna have like not A and B, and A not B. Yeah, like, is it this actually an OR? I think.
Yeah, it's an OR. 'Cause
Yes.
actually, yeah,
It's pretty solid.
Link specifically on what the exams to the way we write it, like everything in ones and zeros again, because it's like in zeros again, and that'll be 0, 1, 1, 0. Has the truth table for the very last ones.
So again, any input is.
So if we're thinking in terms of weights,
Oh, for thresholds, you can just pick them. And you can pick the threshold separately for each of the 3 perceptrons. Okay? We're very liberal about thresholds.
Maybe I'm not going to understand on this thing.
Yeah, it looks good. It's a pretty picture.
Anybody got some weights yet? Austin, Eric, you got weights? All right, let's hear your weights.
All right, so we got, for the first line there, we have 1.
Okay.
and the two middle X lines are -1.
Both of them are?
Yeah.
That's nicely unambiguous.
And then the bottom one is 1,
Okay,
and the other two are 1s.
okay. So why don't you explain the concept behind the weights?
Yeah, so so we wanted to do not ands for both of them. So we have -1 and negative. It's kind of like the logic gate of XOR. Kind of looks like that.
I mean, that is what
Yeah.
we're trying to do, yes.
So like when we design that in CSO, we have to do a not and for each one of those. We put the knots on the
Right,
one
so,
not going one direction, one not going another direction.
so this -1 is a not.
Yeah.
So you're saying, not B and A.
Mhm.
Okay? And then you're saying not A and B.
Mhm.
And then what about this?
And that's anding both of those.
We need to order them instead.
And that's dependent, I think, on the threshold.
Right. So obviously, as you can see, the thresholds are kind of a tricky issue. Here's how we address the thresholds in practice. We actually add the thresholds as an additional input. So the tradition is to use the value -1 as like a fixed input value. And then you've got an additional third weight coming in that's multiplied by that -1, and that's your threshold weight. So what happens is by starting with a -1, you've got a value here that is subtracted from the sum of the other inputs that moves it down towards 0, or obviously up if you make it a negative weight. So each of these then actually has a threshold represented as just this additional input. And that way, during the training process, that weight gets adjusted just like all the others, and it can move that line around and really help it be flexible. So cool. So we can actually do this then if we go to 2 layers, can't we? Everybody on board with this, or we need to go over this in some more detail?
I think we have to understand instead of adding this like -1. Why should we again add this -1?
Oh, it's so we can change the threshold. Yeah, Mitchell.
I get double if like they were in or
Yeah.
gates, but I don't understand how that relates to the weights.
All right, so let's walk through this in detail then to make sure that's as clear as possible. So let's do the truth table for exclusive OR. Okay, so let's calculate. Let me shrink this down so we can see it. And let's actually calculate it for each of these possibilities. Let's look at what numbers we get. Forget about the threshold inputs for now. Let's just look at the raw numbers. So if I put zeros into both of these, I have zeros at both of these stages, right? Because I've multiplied all weights by 0. And then I've got 0 times 1 plus 0 times 1. So what I calculate is a 0. That one's easy to see. The others, we might have to be a little more careful. And then let's label this. So in 1, in 2. So we can ignore in 2 because it's going to be 0. Let's focus on in 1. In 1 puts a 1 over here and a -1 down here. That then gives us a 1 and a -1, and whoops, we got 0. So what did you want to do with the threshold at that point?
I don't know if we're using the same definition.
Well, we're kind of in trouble, aren't we?
Yeah, it looks to be that way.
So we need to find the error and fix it. Or maybe there's something we could do with those thresholds, right? Because and actually, I kind of hand wave past the threshold. We actually threshold these things before we move on to the next step. So let's back up and look at that, right? So where do you want to set the thresholds? Do you want to just set them at 0, at 1/2, at 1? What do you want to do? Half?
Sounds fine.
Okay. So we're going to put, well, I'm erasing. All right. I'm going to put a 1/2 here and a 1/2 here. All right. And now let's see what happens. A 1 comes in here. And then that 1 gets added to a 1/2. This is a 1/2. Down here, a -1 comes in. -1 times a 1/2 is -1/2. Okay. So now we move over here.
So why are we just ignoring input 2?
Because it's 0. Yeah. Oh, wait a minute. Actually, no. This is -1/2. That took it down to a 1/2. This was already -1. Now it's -1.5. And so let's say it only activates at 0 or higher. If it activates at 0 or higher, and so in effect, if we say it always activates at 0 or higher than 0, that's a little cleaner. Say it activates at higher than 0. So what we do if it activates at higher than 0 is we ignore this one and we activate that one. So this is sending a 1, this is sending a 0, and we do actually get a 1 at that point.
So is that to say that those two
The two middle ones.
their threshold is 0?
Well, the threshold is always 0. What we do with this is we just can subtract the value from the sum in order to adjust the effective threshold. The idea is a little confusing, but once you get the hang of it, what you realize is if you just say the threshold is 0, and then you've got this extra threshold input that alters the sum and moves the sum in a linear way, then you can effectively be changing the threshold. So once you've exceeded a 0, then this activates. So then the other one's going to work the same way, right? Because the other one's going to come in, and 2 is going to be a 1. So that's a positive 1 there. 1's going to be, and then a -1 there. This is going to be a 0. Bam, we're not going to exceed 0 on this one, but we do there, and we get a 1. And so finally what happens is, if they're both 1s, they actually both wind up adding up to 0s. And actually, we didn't even need to adjust the thresholds. I'm going to set these at 0. We didn't really need them.
But that's there for us to use if we.
It's there for, the training algorithm to leverage, But we don't really need them here. So we have 1 plus -1 is 0 in both places. It doesn't activate, and we're at 0. And the beauty of it is we now have exclusive OR.
And our inputs are going to be, and it could be anything. And this is just an example for this, but.
Typically, the inputs are 1s or 0s.
Okay.
So if you're imagining classifying the images, which you'll be more than imagining once you start this project, incidentally. You can imagine that whether a given pixel value is on or off becomes a network input. So if I give you a 25 by 25 black or white image, then your neural network is going to have 625 input nodes. Please forgive me if I don't do an example by hand. Now, what if you've got color images? Well, what you can do is stuff like take the pixel values, the 24 bits that describe each pixel in binary, and make all 24 bits input nodes for every pixel. So if you have, say, a 10 by 10 image, and I set a 10 by 10 image in color to make the math easy, you have 100 times 24, 2,400 input nodes. If it's bigger than 10 by 10, you have a lot more input nodes. You might have so many input nodes that you do stuff like leave a few out. Yes, David.
If it's black and white, and the pixel values are not on or off, and they're between 0 and 1.
Right. Then, so imagine there are 8 bits grayscale. So you get 0 to 255 intensity levels. For each pixel, you make all of the 8 bits literally the input for that pixel. Right. So yeah, again, if you've got a 10 by 10 grayscale, 8 bits per pixel, then you're looking at 800 input nodes. And
Separate each bit of 1 pixel.
so neural networks demand a binary encoding of the data. Whatever data you're going to give the neural network, you've got to encode it in binary. That's just a way to do it. Now, if you only had a single layer perceptron and you're trying to represent something like the situation with the 8-bit inputs, it would be impossible for it to meaningfully distinguish the relative importance of some of those bits. But with 2 layers, you can actually kind of do anything. Depending, of course, on the number of these guys you've got. So when thinking about, so is everybody clear on this concept up to here? This stuff can be horribly confusing, and it's about to get worse. But yeah, innocent. Yeah.
When you gave us an exercise to find weights for this XOR gate
Yeah.
or something,
Yeah.
there is this assumption that you made, like when you were solving it in like
Yeah.
together, about like saying if it's bigger than 0, then we activate. Less than 0, we don't activate.
Yep.
What is the assumption? How do you call it?
A threshold.
And then is that like a standard assumption, or you can change it depending on the situation?
Effectively, you can change it by altering the weight on these -1 threshold inputs. Right. So let's just say, and keep in mind, this threshold idea comes from trying to model the idea of a neuron being active or inactive. Okay. So what we have here then is a situation where, let's say this is a 1, so we're subtracting 1 from everything. So if the sum is 0.5, you subtract 1, it goes to -0.5. It won't activate. Why? I put a 1 here, and 0.5 wasn't greater than 1. So this is just that basic exercise of saying, checking whether x is less than y is the same thing as checking whether x minus y is less than 0. And that's why we use a -1 threshold input right here. Great question. Other questions so far? Okay. So we're going to move ahead to the next stage, which is how to think about training these things. And that was the great innovation. When you're thinking about training these, the issue is figuring out how do you award credit to or punish the weights in this first layer. Second layer is easy. You just check against the outputs. The first layer is less easy. You know, working backward, how do you give credit for the different inputs depending on what happens out there? So this led to what's called the backpropagation algorithm, which I'm going to go over the concept for you now. So the basic idea of backpropagation is to say, if I want to figure out how to assign credit for my inputs, what I can do is just treat this thing as a function of multiple variables, where each variable is just an input. So it's like this would be a function of x comma y. And then what I can do is calculate the derivative of that input value and use that to determine the error. So why the derivative? So as you all remember from calculus, right? Well, somebody tell me, what is the derivative? You know, when we think about calculus. What's that?
Instantaneous rate of change.
It's the instantaneous rate of change. Exactly. So what we can do is we can use the derivative of not only the output node of the network, but the derivative of these so-called hidden nodes to determine which direction should these weights be changing. Which direction should they be changing? But here we run into a problem. Namely, if you think about the zero threshold function we've been using, where any x value below 0 is a 0, and then everything up there is a 1, right? Can you take the derivative of this function? Sadly, no. Why not?
It's not
There's no
continuous.
It's not continuous. So what can we do? Well, we can find a function that looks like a threshold, but is continuous. So let me give you a sense as to what that ought to look like. Right? Little asymptotes. One along the x-axis and one at y equals 1. Then what we want is for it to look something like this. Fortunately, such a function exists. It is called the sigmoid. But what's really great about the sigmoid is its derivative. Its derivative can actually be calculated as itself times 1 minus itself. So if you got some sigmoid of x, you want to find the derivative of it, it'll actually be sigmoid of x times 1 minus sigmoid x. So where that really helps us in thinking about the backpropagation process is that what we can do is use the output of the network as it stands to actually calculate its own derivative. And you know that you'll have a nice well-defined value because of the asymptotes at 0 and 1. Because it's got asymptotes at 0 and 1, you know you're going to get values that are in this bounded 0, 1 range. I am doing horribly on time. I'm probably not going to finish today. So what I'm going to do is I'm going to record either later this afternoon or tomorrow morning the stuff I didn't get to today and also explain the assignment. So the assignment will go out tomorrow and so forth. And I'll also have a few extra, a bit more of an explanation of how exactly backpropagation works. So, and I'll explain the assignment there. I'll briefly summarize. You're going to be doing handwriting recognition. And to add to the fun, you are going to create your own examples. So I've got a fun little graphical user interface that lets you draw handwriting examples. And so you're going to build your own little repository of labeled examples and then train your network to recognize them. So like I said, I'll demo that for you later. For now, I did put up some notes on the website, which I'll have a link to once I have the assignment posted, that summarizes algorithmically how you're going to go about the learning algorithm. And so I'm going to show that to you now. Here we go. So perceptron, so we talked about this. It's a two-layer directed weighted graph where the first layer is the input nodes and has that special threshold input, right? And then the second layer are the output nodes. So how do you compute an output? And here I've gone straight to the sigmoid. For each output, for each input with an edge to that output, multiply the edge weight by the input value, and then add them all up. Then you threshold the output using this sigmoid function, which is 1 over 1 plus e to the minus x. So just to go back here, sigmoid should have actually just told you except I can't even write the number 1. That's the sigmoid function, okay? And its derivative happens to be its own result times 1 minus that. You'll have to forgive me for not deriving it in class. So you threshold the output, that sum, using the sigmoid. And then if f of x is the sigmoid of x, f prime of x is f of x times 1 minus f of x. So using the sigmoid, you can train it as follows. For every one of your input-output pairs, you apply the network to the input. In other words, kind of like we were doing earlier with our examples, we take those input values and multiply them by their weights. Then for each output, you compute the error, which is the target output minus the perceptron output. Then you multiply the error by the learning rate. So that's the 0 to 1 value we discussed that keeps it from kind of flip-flopping all over the place. And then the gradient is just a fancy word for partial derivative. So the derivative of one variable in a multivariable function. So when you see gradient, you can just think derivative and life is good. But the way people talk about this in literature, it's always gradient, because that's the technical term for it. The gradient's like the collection of all the partial derivatives for a given function. So the gradient input is calculated using the output value. In other words, you multiply it by this. You have the error times the learning rate times the output times 1 minus the output. And that's your gradient. Then for every one of the weights, you multiply the input value by the sum of all of these gradients, add that result to the weight, and don't forget to update your threshold. So what does backpropagation fit into this? So I think of this multi-layer perceptron as 2 perceptrons, one stacked next to the other. Okay? A lot of people call it 3 layers because you've got the input nodes, the hidden nodes, and the output nodes. If you're counting by ranks of weights, it's 2 layers. If you're counting by ranks of nodes, it's 3. My personal preference is to think of it as 2. Many have other preferences, and so I just want you to be aware of that distinction. So the first layer are the inputs, the second layer are the so-called hidden nodes, the outputs of the first, and simultaneously the inputs of the second, and then you've got those output nodes. So computing the output is straightforward, and we walked through that. You compute the outputs for the first perceptron using those outputs. Those are now the inputs for the second perceptron. So what about this idea of backpropagation? You first train the second perceptron with a particular example. You next calculate the errors for each of the hidden nodes. Now for each output node, and when I say output node, I mean for that first perceptron. In other words, hidden node here. I'll edit this to make that super clear. Add to the total error the product of the weight from the edge from the hidden node to the output node, the gradient of the output of the input to hidden perceptron, and the error from the hidden to the output node. And then you modify each incoming weight as you did with the perceptrons. So that's the structure of the algorithm. Fans of linear algebra might recognize that what we're really doing is kind of a chained vector multiplication. And you'd be right. Neural networks, in the end, are just a big pile of matrices. So, like I said, I didn't manage time so well today, so I'm going to make up for it. I'm going to do some supplementary video to explain the assignment. You should have that by tomorrow morning, by mid-morning, roughly, tomorrow, assuming I can actually estimate my timing better than I did during this lecture. Any last questions on what we covered today before we wrap up? Yeah, Silas.
When you were talking about the gradient,
Yeah.
when you're saying x, was that the output value?
X you can think of x as an input. F of x, the output, is the sigmoid of that input. And so once you've got that f of x, you multiply it by 1 minus itself, and that gets you the gradient. So yeah, these guys back in 1986 were really, really clever. They came up with a function that looks a lot like a threshold, but when you find the derivative, is super easy to calculate. So like, you won't be writing any code that does calculus. You'll be writing code that uses it. But it won't actually be doing it, which is kind of a relief. And so there it is. So like I said, sorry I didn't quite get as far as we needed to in the lecture, but I'll make up for it, do a little recording, and you all can follow up on that. And then for Tuesday, once I post the assignment, which I'll do once I've got that last video up that explains the assignment, at that point, you'll know that you've got a little presentation to do on Tuesday, and then we'll look at our results on Thursday. So it'll be a lot of fun. I'm going to have you, like I said, create your own data samples, and we'll just see where it goes. See you Tuesday, if not before. See you virtually well before.